This is a video for AQA Further Pure Mathematics. Matrices, section 5.4, where we're finding eigenvectors and eigenvalues for 3 by 3 matrices. In previous videos we've seen how the characteristic equation, the determinant of m minus lambda I is equal to 0 vector, is found, and how we use that in a 2 by 2 situation. So now I want to consider 3 by 3 matrix, and of course the characteristic equation is exactly the same, but we end up with a 3 by 3 determinant to evaluate. Here you can see that I've subtracted lambda from each of the elements on the leading diagonal to give the determinant equal to 0. Now there are all sorts of different ways of evaluating that determinant, but one way would be to see that if we take row 2 and 3 and add them to the first row, that the first row becomes 4 minus lambda in every single element. The second rows, of course, don't change. Neither does the third row. But that means that we can then take out 4 minus lambda as a factor from the top row. And further from that, if we now subtract that top row from each of the second and third rows, we get the following, where we're subtracting 1 from every element in each of the second and third rows. So the first row is still 1, 1, 1, but the second row becomes 0, 1 minus lambda, 0, and then 0, 0, 1 minus lambda. Now crucially, this has got zeros in the first column, so I can evaluate this determinant by using the 1 multiplied by the determinant of this block here. So we end up with that meaning that 4 minus lambda, and if you look at the determinant of the little 2 by 2 block, it's 1 minus lambda all squared. That must be equal to 0. So our characteristic equation in this case is 4 minus lambda, 1 minus lambda all squared, equal to 0. So just looking through that again, then the characteristic equation comes from m minus lambda I equal to 0, the determinant of that equal to 0. You could evaluate that determinant by taking each element multiplied by the 2 by 2 block in the usual way, but doing some row manipulation allows us to come down to this rather simpler 3 by 3 determinant here to evaluate. So we end up with the cubic as we would expect for a 3 by 3 matrix, but in this particular instance we end up with only 2 distinct eigenvalues. In general you'd expect 3 eigenvalues, but here we have a characteristic equation where there's a repeated factor, so there are only 2 distinct eigenvalues, 1 and 4. Once we've got the eigenvalues, then we can find the eigenvectors by using the equation that m minus lambda I multiplied by the eigenvector must be equal to a 0 vector. So taking first of all the value lambda equal to 4, then subtracting 4 from each of the elements in M on the leading diagonal gives a matrix which is negative 2, 1, 1, 1, negative 2, 1, and 1, 1, negative 2. And that's multiplied by the eigenvector x, y, z that we're trying to find, and that must be equal to 0 vector. Now remember, we want to find a eigenvector or an eigenvector, and so we can let x be equal to 1 and find the particular eigenvector which has x equal to 1. So substituting that into our matrix and multiplying out the matrix, we get the following. Taking the first line, we get minus 2x plus y plus z must be equal to 0. So that's multiplying that line by the column x, y, z. And then taking the second row, we get 1 minus 2y plus z must be equal to 0. That gives two equations that we can solve for y and z. Y turns out to be 1 and z is also equal to 1. So you just check those numbers in those equations to make sure that you're happy that they're correct. And therefore, an eigenvector is the vector 1, 1, 1. So to find the eigenvector, we take the particular eigenvalue, in this case lambda equal to 4, substitute it into this equation, and then that produces a set of equations for the eigenvectors, the values of x, y, and z. But we can, without loss of generality, take x equal to 1 to find the particular eigenvector at the end where x is equal to 1. Similarly then, if we have lambda equal to 1, then the matrix is as shown when we substitute m minus lambda I times v. And again, we can let x equal to 1. So we end up with this matrix, and you can see that all rows are going to be the same. They all give 1 plus y plus z is equal to 0. So here we can say, well, let's look at when y is equal to 1, and therefore z would be equal to negative 2. So the eigenvector here is the eigenvector 1, 1, negative 2. So this is quite unusual that we had just one equation coming out from the matrix multiplication. In general, of course, you would find two equations here that you would have to solve simultaneously. The other thing that was quite different about this particular case is that there were only two distinct eigenvalues. So we found that for this matrix there were two eigenvectors and two eigenvalues, so the corresponding eigenvalues. In general, for a 3 by 3 matrix, you would expect there to be 3 eigenvalues and 3 eigenvectors in general. That's the end of this video looking at the eigenvectors and eigenvalues for 3 by 3 matrices. In the next video we'll be looking at the idea of diagonal matrices.